Hello everybody, and welcome to our video on applications of Taylor polynomials and approximate integration. So scientists, particularly of the computational variety, often use Taylor polynomials to approximate functions. Recall that the nth degree Taylor polynomial at a is given by the sum from I equals 1 to n of the ith derivative of f at a over I factorial times x minus a to the I power. So not only do scientists typically use these kind of Taylor polynomials to approximate functions, they also are how we compute the values of most functions that you evaluate in your calculator, except for the basic algebraic functions. So there are three possible approaches to estimating the size of the error in a Taylor polynomial. And that's to one, graph the remainder function and estimate the error. Of course, this is a pretty silly thing to do, because if we had a perfect graph of the function, we could probably just use that to estimate the values anyways. So not too worried about that. Second, if the series is alternating, we can use the alternating series estimation theorem. And we've seen in the past how powerful that theorem is. But in all cases, we can use Taylor's formula, which says that the remainder is equal to the n plus 1th derivative at z divided by n plus 1 factorial times x minus a to the n plus 1 power, where z is a number that lies between x and a. Okay, so let's go ahead and tackle an example. So we're going to approximate f of x equals the cubed root of x by a Taylor polynomial of degree 2 at a equals 8. So this is really nothing different from what we've been doing so far, except that we're actually stopping. Most of the time in our previous section, we tried to find a full Taylor series for the expression and figure out what all of its terms looked like. But it's not always easy to find the patterns that would give you a general expression. And it's also not always necessary. Oftentimes we just need a few terms of the Taylor polynomial. And so that's what we're going to do here. So just like before, I'm going to set up my chart. So we'll have n, the nth derivative of f, and then whatever happens when we plug in a, which in this case is 8, to that nth derivative. And we only need 0, 1, and 2 for our values for n, because we're looking for a polynomial of degree 2. Okay, and let's go ahead and compute those derivatives. So first of all, f of x is the same thing as x to the 1/3 power. So when we take the first derivative, this is 1/3 x to the negative 2/3. And when we take the second derivative, we get negative 2/9 times x to the negative 5/3. And now I am going to rewrite those slightly as I put them to my chart. Instead of x to the negative 2/3, I'm going to write this as 1/3 times the cubed root of x squared. And then for my second derivative, I'm going to write that as negative 2/9 times the cubed root of x to the 5th power. Okay, so now I'm going to plug in 8 for each of these, and the cubed root of 8 is just 2. And here we get 1/3 times the cubed root of 8 squared. So that's 1/3 times 2 squared, which is 1/12. And for the second degree term, we get negative 2/9 times 2 to the 5th. And if we plug in 8, we get, or if we plug in 2 to the 5th, if we plug this all into a calculator, I'm going to just skip that and say, hey, this works out to be negative 1/144. Okay, so now that I've got that, I can write out my expression for my second degree Taylor polynomial. And that's my zeroth coefficient times x to the 0 over 0 factorial plus 1/12 times x to the first over 1 factorial plus a negative 1 over 144. And I put x to the 0 and x to the first, so I'm off to a great start with that typo. This should be x minus a, which in this case is 8 to the 0 power, and x minus 8 to the first power. And then the next term should be x minus 8 squared divided by 2 factorial. So our standard Taylor formula, but we just stop at the second degree term. Now we'll do a little bit of cleanup here. 2 to the 0 power is 1, over 0 factorial is 1, so this is 2. 1/12 divided by 1 factorial. It's still just going to be divided by 12, with x minus 8 up top. Plus, or I should say actually minus, 1 over 144 divided by 2. That's going to be negative 1 over 288. And this is x minus 8 squared. Okay, so there's our Taylor polynomial of degree 2 at a equals 8. So now we ask ourselves, how accurate is this approximation when x is between 7 and 9? So recall that for the remainder formula, all right, we want to know, okay, what's the absolute value of the remainder? Well, our remainder formula is the n plus 1th derivative, so in this case it'd be the third derivative of x, I should say of z, times x minus 8 to the third power over 3 factorial. So I need to know what my third derivative of f is. So I'm just going to real quick look back up here at my second derivative, and negative 2/9 times negative 5/3 becomes 10 over 27 times x to the negative 8/3. So I put that into my formula, and I get 10 over 27 times the cubed root to the 8th power of z, in this case, times x minus 8 to the third power over 3 factorial, which is 6. Okay, so now I'm going to try to simplify this thing a little bit. So I'm dividing everything by 6, so I can simplify the 10 over 6 to be 5 over 3. And 3 times 27 is 81. And now we're going to try to find some upper bound on this expression. We obviously can't evaluate it directly because we're asking a, in general, for what values between 7 and 9 for x, or how accurate is the approximation within that range, I should say, the values between 7 and 9. But we also don't know what z is. Now what we do know is that if x is between 7 and 9, z also has to be between 7 and 9, because z is always between the center of the series and x, and the center of the series is 8. So that allows us to figure out some bounds. And the way students should do this, in my opinion, is one little piece at a time. So first, I know that x minus 8 cubed takes its largest value when x is 9 on this interval, right? It increases the bigger x is. So this is going to be at 9 minus 8 cubed. So anything else except for x being 9, it's going to be smaller, right? And then we'll still write over 81 times the cubed root of z to the 8th power. 9 minus 8 is 1, 1 cubed is 1. So this all boils down to 5 over 81 times the cubed root of z to the 8th power. And I could drop the absolute value there because the cubed root of z to the 8th power will be positive. Now, I'm asking what value of z will give me the worst case scenario, the biggest this could possibly be, the worst the error could be. So if we think about when we divide by a number, if we're dividing by a smaller number, the result is bigger than it would be if we divided by a bigger number. So I'm looking for the smallest value of z in this case. And so this is less than or equal to 5 over 81 times the cubed root of 7 to the 8th power. Okay, so that gives me an upper bound for the whole expression, and when you plug this into a calculator, you get approximately 0.00034. And so, yeah, that's what this says. This Taylor polynomial is going to give me accuracy of out past the third decimal place as long as I'm in the interval from 7 to 9. All right, so let's take a look at another example. What is the maximum error possible in using the approximation sine of x is approximately x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, when x is between negative 0.4 and 0.4. So this is the 5th degree Taylor polynomial for sine, and it's centered at a as 0. All right, so this is the 5th degree Taylor polynomial at a equals 0. And so that means if I want to find the error associated with this, I need the 6th derivative at z times x to the 6th power over 6 factorial. Okay, so since we're talking about sine of x, the 6th derivative for sine, well, let's go through it. Sine is the 0th derivative, so cosine is first, negative sine is second, negative cosine is third. Then we're back to sine is fourth, then cosine is fifth, and finally negative sine of x is our 6th derivative. So this becomes the sum from the absolute value of sine of z times x to the 6th over 6 factorial. And how do we bound this? Well, another thing I want to emphasize here is that every component of these terms that you try to bound, you should do on a case-by-case basis. A lot of students will get tripped up and think that they should always be plugging in numbers in order to find their bounds. Because, hey, I did one example where I plugged in numbers, and one of them I plugged in the bigger number, and the other the smaller number, so it's got to always be one of those things. But that's not what we're doing. We're analyzing each component function on a case-by-case basis to figure out how to bound them, and that's why I do it one piece at a time. So when I look here, I look at negative sine of z, and I go, well, I know that sine is always less than or equal to 1. Which tells me that when I take the absolute value of this whole thing, it's always going to be less than or equal to 1 times x to the 6th over the 6 factorial. But of course, these terms are all positive. So this is x to the 6th over 6 factorial, which is 720, I believe. And the worst case scenario here is going to correspond to the biggest value for x to the 6th. So I want to point out here, since x to the 6th is an even power, it actually doesn't matter if you plug in negative 0.4 or 0.4 in this case, because the magnitude is going to be the same. When I raise it to the 6th power, I'm going to get the positive value in both cases. So it doesn't matter which one I pick, but for ease, I'll just pick 0.4 to the 6th. And when I plug that into a calculator, I get approximately 0.000057. So that's a pretty good approximation on that interval, I would say. All right, now we're going to use this approximation to find sine of 14 degrees. Now, there's something a little bit subtle here that's easy to trip anyone up, which is that when we talk about Taylor series for sine and cosine, just like when we talk about derivative formulas or integral formulas for sine and cosine, these things were all derived under the assumption that we're working with radians as our measure for our angles. So if we try to use this approximation for sine of 14 degrees, that's going to be no good. We've got to convert 14 degrees to radians. So 14 degrees times pi radians over 180 degrees. That's going to convert us into radians, and we get approximately 0.24435 radians. Okay, so now that we have radians, we can actually use this to evaluate. And this is why your calculator has that pesky radians versus degrees issue, because it has to actually convert. If you're in degrees, it has to know to convert to radians before it tries to evaluate using the Taylor series. Okay, so with that said, let's plug it in. So all this says is, that means that sine of 0.24435 radians is approximately, let me just zoom out a touch here so I can get that on the screen, is approximately 0.24435 minus x cubed over 3, that's 0.24435 cubed over 3 factorial, I should say, which is 6. Plus x to the 5th over 5, that's 0.24435 to the 5th power over 5 factorial, and 5 factorial is 120. Okay, and we plug that all into a calculator, and we should get approximately 0.24193. Now, of course, if you recall from pre-calculus how we would get values for the trig functions that weren't on the unit circle, we'd have to use sum formulas or difference formulas or half-angle formulas, etc., so forth and so on. And this is the power of what Taylor polynomials do for us, is we don't need all these formulas that are really computationally expensive, and we'd be doing hundreds of computations to get one new angle added to our list. Instead, we can just go, hey, we know this little polynomial with 3 terms, just plug the number into that. Makes things a whole lot simpler. All right. Now part C, for what values of x is this approximation accurate to within 0.00005? Okay, well, the absolute value of r sub 5 of x is the absolute value of negative sine of z times x to the 6th over 720, as we saw before, which is less than or equal to x to the 6th over 720. But this time we want to know which values of x will make this less than 0.00005. So I multiply the 720 across, and that gives me x to the 6th is less than 0.036. And that gives me that the absolute value of x, when I take the 6th root of both sides, is less than 0.57462. So in interval form, that's x between 0.57462 and negative 0.57462. Okay, that's it for that one. Let's move on. So example 3, in Einstein's theory of special relativity, the mass of an object moving with velocity v is given by mass equals m naught over the square root of 1 minus v squared over c squared, where m naught is the mass of the object at rest and c is the speed of light. In other words, what Einstein's theory says is that when this v squared approaches c squared, so this denominator is going to get smaller, so we'll be taking 1 minus something approaching 1, and so the mass of the object actually changes relatively. So what we're going to look at really here is how this compares to its relationship with Newton's physics and its treatment of mass. So the kinetic energy of the object is the difference between its total energy and its energy at rest. We have that K, the kinetic energy, is mc squared, mass times the speed of light squared, minus the mass at rest times speed of light squared. So we want to show that when v is very small compared with c, this expression for k agrees with the classical Newtonian physics, which says that the kinetic energy of the object is 1/2 the mass at rest times v squared, the velocity of the object. So essentially what we're saying is, so when this says show that when v is very small compared with c, we're actually saying we're showing that Newtonian physics is actually an approximation of Einstein's theory. So I think that's really fascinating to see that. So we got more information, we got more complex modeling of the world of physics around us, that what we see is that Newton's laws were still valid as approximating measures of the world around us. So they were pretty close. All right, so let's take a look here. So kinetic energy, that's mc squared minus m naught c squared. So here we're going to substitute in Einstein's expression for mass, m naught over 1 minus v squared over c squared. And so now we can take this expression and we can factor out the m naught and the c squared. And we get m naught c squared times 1 minus v squared over c squared to the negative 1/2 power. Right, we moved that from the denominator into the numerator, so we made the power negative, minus 1. And so now we can use the binomial series, with x being equal to negative v squared over c squared, to express this as the sum from n equals 0 to infinity of negative 1/2 choose n times negative v squared over c squared to the nth power. And when we expand that, looks like the following. 1 plus 1/2 v squared over c squared plus 3/8 v to the 4th over c to the 4th plus 5/16 v to the 6th over c to the 6th plus ... So I'm obviously not going through every little plugging in of every number here because we've done this kind of work before. I just want you to see the big idea here. Okay, so what does that tell me? Well, that implies that this expression we had before for the kinetic energy, which we rewrote in this way, m naught c squared times the binomial expression minus 1, that can be rewritten as follows. M naught c squared times the, in brackets, this expansion of our binomial series minus 1. So the 1 minus 1 cancels, and we get m naught c squared times 1/2 v squared over c squared plus 3/8 v to the 4th over c to the 4th plus 5/16 v to the 6th over 6 to the 6th plus blah, 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 blah. We multiply the m naught c squared across, and we get m naught over 2 v squared plus 3m naught over 8 v to the 4th over c squared plus so forth and so on. And the whole key here is that if the velocity is slow relative to c squared, these are going to be really small because the speed of light is really big, right? So if you're moving 100 miles per hour on Earth, that is nothing compared to the speed of light. And that means this fraction is going to be incredibly tiny. And that's going to be true for all of these fractions dividing by the speed of light to a power. And so all of those other terms are going to be very close to 0 overall. And that's why we can say that this is approximately m naught over 2 v squared. So I think that's really cool. I hope you enjoyed taking a look at that. But let's go ahead and move on to approximate integration. So I've blended these two sections into one because they both deal with approximation techniques, but these are very different approximation techniques than dealing with the Taylor and Maclaurin series. And so I do want to be clear that the Taylor and Maclaurin series are much more powerful approximation techniques in general and give us a lot more important tools in advanced mathematics than these approximation techniques that we're about to touch on. But these approximation techniques are also fairly computationally simple, so they can still be quite useful when it comes to using computers to compute things. They don't require as much human intervention, I think, as dealing with Taylor polynomials and Maclaurin series do. Okay, so anyways, let's dig in. All right, so we've got the midpoint rule. Now, you probably saw the midpoint rule in your Calculus 1 course, so this shouldn't be new, but it's pretty simple. It says that the integral from a to b of f of x dx is approximately m sub n, which is delta x times f of x1 bar plus delta x times f of x2 bar, so forth and so on. And so what each of these is the width times the height of the, in this case, the first rectangle. And the second rectangle. And what we're doing here, if we look at the picture off to the right, is that we are literally just approximating the area under the portion of curve, so forth and so on. And we're doing it by setting the height of the rectangle. This is the key. The height of the rectangle is being set to the value of the function at the middle of the interval that I drew the rectangle on. So if we take a look here, what's delta x? It's the width. And then f of x1 here is the height of the rectangle. And we multiply them. And then we do that for all of the rectangles, add them together, and that's the whole thing. Now, the way we usually write this formula is we factor out the delta x and put the f of x1 bar plus f of x2 bar plus blah, 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 blah. Okay, so how do we get delta x? Well, that's really, really simple. We take the width of the interval and divide it by the number of rectangles. That's it. You take how long the interval is, b minus a. You divide it by the number of rectangles. That's your width. Now, how do we get our points? How do we compute the points to find the midpoint of the interval? Well, midpoint means average. So how do I find the average of the interval? I take the 2 points on the ends, so say here and here, I add them and divide by 2. And that's it. So if we look at here, I've got 0 and 2. So if I add them, 0 plus 2 is 2, and I divide by 2, I get 1, which is the midpoint of the interval. Okay, so that's what the midpoint rule is. Now let's take a look at the trapezoidal rule. The picture looks a bit different for the trapezoidal rule. So we say the integral from a to b of f of x dx is approximately t sub n. And t sub n we write as delta x over 2 times f of x naught plus 2 f of x1 plus 2 f of x2 plus ... plus 2 f of x sub n minus 1 plus f of x sub n, where delta x is b minus a over n. And this time x sub I is the endpoints of each interval, a plus I delta x. So we're going to look at this one a little bit more closely because it's not quite as obvious. This is called the trapezoidal rule because you are quite literally using trapezoids to approximate the area under the curve. So what we do is we take a point on each side of the interval. We draw a line segment between it, and then the trapezoid that gets formed on that interval from there to there is our area. So if I turn this trapezoid sideways, it's going to be a little easier to see how we get our formula. Okay, so notice this down here is delta x, so I turned the formula sideways. And so delta x actually becomes the height of my trapezoid. And so this height here on the graph, that would be f of x. In this case, it's f of x2, but we'll be a little more general, f of xi. And then the second one is f of x I plus 1. And so that means that this base has length f of xi, and this one has f of xi plus 1. And so if I want the area for this thing, and we'll call it the area sub I get the sum of the bases divided by 2, the average of the bases, and then I multiply by delta x. Okay, so now how do we get the general formula? Well, we add up all these trapezoids. So that means the total area is approximately, okay, I get f of x0 plus f of x1. That's going to be my first trapezoid divided by 2 plus my second trapezoid. So that's f of x1 plus f of x2. I forgot my delta x there. Plus f of x2 over 2 times delta x plus f of x2 plus f of x3 over 2 delta x plus ... And at the end, I'm going to add f of x sub n minus 1 plus our last term, f of x sub n, over 2 times delta x. And so now I can factor out the 1/2 and the delta x, and I get delta x over 2 times f of x naught plus f of x1 plus f of x1 again plus f of x2 plus f of x2 again plus ... And what we see at the end here is that every term will show up twice in this sum except for the first and last term. The others all show up twice because they are part of the formulas for at least, or for 2 of the trapezoids in the expression. So that's why when we look at this formula, we see that the simplified form of the formula is delta x over 2 times f of x naught plus, and then all of the middle terms have to be multiplied by 2, and then you just get the last f of x sub n. All right, so that's why the trapezoidal rule works and what the trapezoidal rule is. Now this x sub I is a plus I delta x. Again, something we hopefully have seen in Calc 1, but if we take a look at this example here, so x sub I would be 0 plus I delta x. So, and delta x is 2, the width of these intervals. So I times 2. And so if we look at our values for I, what's x1? It's just 2. And when we look here, that's what we labeled f of x1. When we look at x2, what do we get? Well, 2 times 2 is 4. So that's 4. So f of x sub 4. Or f of 4, I should say. So all that is taking our delta x and moving us over by delta x each time we increase I by 1. All right, so let's move on and tackle one quick definition and an example. So definition, the error in using an approximation is defined as the difference between the exact value and the approximation. In other words, if you know the actual value of the integral, and I ask what the error is, you just subtract the approximation value versus the actual value. That's all there is to do. Okay, so with that being said, we're going to use both the trapezoidal rule and the midpoint rule with n equals 4 to approximate the integral. And so to start, since I'm going to need the same delta x value for both the midpoint and trapezoidal rule, let's figure out what delta x is. So delta x is b minus a over n. So this is 4 minus 2 over n, but n is 4. And that's 2 over 4, which is 1/2. Okay, so we've got delta x. Okay, so now we'll start with the trapezoidal rule. Doesn't matter which one we start with, but we'll start with the trapezoidal rule. So to find the trapezoidal rule, I have to know what each of my subintervals endpoints are. So I'm going to draw my interval 0 to 4 and break it into 4 pieces. And so generally speaking, you don't even have to use the formula if your interval is small and it's broken up into a small number of pieces. I'm fine with students just drawing out the interval and figuring out where the pieces are. But if I take this interval, that should be from 2 to 4, not 0 to 4, and break it into 4 pieces. The middle will be 3, and then in between 2 and 3 is going to be 5 halves, and this will be 7 halves. And so those are all my interval points. If you wanted to use the formula, you absolutely could. And of course, you might need to if the value of n was really large or the interval was weird, whatever. But it's not necessary in this case. So if we were to use the formula, x sub I equals a plus I delta x, that's going to look like 2 plus I times 1/2, which is I over 2. So x0 is just 2, and x1 is just 2 plus 1/2, that's 5 halves. And x2 is 2 plus 2 halves, which is 1, which is 3, and so forth and so on. But I already figured that out in the picture, so I didn't really need to do that. I just wanted to illustrate, hey, you can just set up that formula, plug and chug, and you're good to go. Okay, so now let's go ahead and try to apply the trapezoidal formula. And a little bit confusingly, we use similar notation for the trapezoid and midpoint rule formulas as we do for Taylor series and Maclaurin series, but that's okay. So T sub 4 is delta x over 2 times, and I start with, and I'm looking at each endpoint of my subintervals here. So I start with f of 2 plus, and then I double f of 5/2. And I double every other function value at these interval endpoints until I get to the last one, which is just f of 4. So when I've got a student doing a problem like this, there's a few things that I want to see explicitly, just so that I can see that they understand all the concepts at play. So the first thing I want to see is delta x explicitly solved for. And then I want to see all of the sample points that they need. So if they draw it with the interval to find the values, totally fine. If they instead use the formula, either way, that's fine. But I want to see that. And then I definitely want to see this formula written out explicitly, and I want to see all the values plugged into the formula. So delta x, of course, is 1/2, so this is 1/2 divided by 2 over, and then f of 2 is 3 times 2 squared, plus 2 times f of 5/2, which is 3 times 5/2 squared. Again, I'm just plugging into the function in the integral here. Plus 2 times f of 3, which is 3 times 3 squared, plus 2 times f of 7/2, which is 3 times 7/2 squared, plus f of 4, which is just 3 times 4 squared. So I also want to see this. As long as I've got all of this information and a final answer, I'm fine. If at this step a student wanted to plug all of this into a calculator and just spit out an answer right there, I'm totally okay with that. But I want to be able to see that they understand how these formulas are set up, how you apply these trapezoidal and midpoint rules. With that being said, I actually think that a lot of times, working through a little bit of the algebra in these problems makes them easier to plug into a calculator without making a mistake. So I'd prefer, or at least I think it's worthwhile for you to at least consider if it would be easier to simplify first. So what do I mean here? Well, 1/2 over 2 is 1/4. That's certainly going to be less weird to put into a calculator. I also notice that every single one of these terms has a factor of 3 in it. And so I can factor the 3 out. And then what do I get left? 2 squared is 4. 2 times 5 over 2 squared. That's 25 over 4 times 2. So that's 25/2. Plus 2 times 3 squared. That's 18. 2 times 7/2 squared. That's 2 times 49 over 4, which is 49 over 2. And then plus 16 at the end here. So at that point, I can combine everything inside this fraction together. I get 3/4 times, and my whole numbers are all going to come out to be 38. 4 plus 18 plus 16. And then I've got the 25/2 plus 49/2, and 29/2 plus 49/2 is 74/2. And at this point, this simplifies even further. 74/2 is 37, and 38 plus 37 works out to be 75. So this is 3/4 times 75. And that, in my opinion, is going to be a lot less prone to making errors when you're entering it in your calculator than using this, at least this very first form. So generally, I would suggest, hey, take 2 minutes to simplify. Probably will cut down your chance of making silly errors. In any case, we throw this into a calculator and get 56.25 at this point. Okay, so next. Now we're asked to evaluate the midpoint approximation. And so m sub 4 looks like delta x times, and here we just evaluate f at a bunch of endpoints, or a bunch of midpoints, I should say. So x1 bar plus f of x2 bar. And there should be 4 of them. for the midpoint rule, 1 for each interval. Which that's something important to notice here, as one of the differences between these two things. When we look at the trapezoidal rule, there's 4 intervals, but we need 5 different values of the function, and that goes back to this picture before, because we need a sample point from each side of the interval, so we get 5 points total for 4 intervals. Whereas for the midpoint rule, we only need a single point in between each interval, so we should have less terms. We should have actually 4 terms here. Okay, and now the things we got to figure out, well, we know what delta x is. That's simple enough. That's just 1/2. But we have to figure out is what these sample points are, these midpoints. So if we draw our interval again, so this was from 2 to 4. I almost did it again. 2 to 4. So we have our 4 intervals, but what we're looking for, the x values that we want to sample at, are the midpoint values. And so it's not that hard usually to just figure out the midpoints by looking at the interval, right? I might need a common denominator, and since I'm going to divide it in half, instead of being 5 halves, I should maybe think about this in terms of fourths. So 2 is 8/4, and 5 halves is 10/4. So in between 8/4 and 10/4, so we've got 8/4 here and 10/4 here. So the midpoint is 9/4. So you can reason through it that way by just looking at, hey, what are the endpoints of my intervals? What's going to be between them? You might have to do a little fraction work. Or we can apply our midpoint formula if you wish to. So xi bar is just the average of xi plus x sub I minus 1 divided by 2. So, for example, if I look for x1 bar, that's going to be 2 plus 5 halves divided by 2, which is 1 plus 5/4, which is, oh, look at that, 9/4. Big surprise. Not actually, but... All right, so point being, I'm not going to compute each of these explicitly, but you can do it either way. You can either use your midpoint formula, or you can just try to look at this interval and see if it's easy enough to figure out what the midpoints are. Okay, so 3 is 12/4, so between 10 and 12/4, that's 11/4. And then the next one will be 13/4, and finally 15/4. So those are our midpoints. So that's what we actually need to plug into our function. F of 9/4 plus f of 11/4 plus f of 13/4 plus f of 15/4. And at this point, I can just start plugging into the actual function. So, and again, the whole thing about what I want to see for this is primarily because I want to be able to make sure students understood what was happening and also get partial credit if they understood what was happening but made a calculator mistake. So a lot of times students will try to jump straight from, they'll go straight from here, 1/2 times f of these things, go straight into the calculator and spit out a value. And if a student does that, I have no opportunity to judge their understanding of the concepts, only whether or not the final answer they got was correct. But if a student sets it up clearly and then writes the function explicitly, plugging the values in, that gives me the ability to say, okay, you understood how to set all of this up perfectly. You made a little calculator error. I don't have to take off much for that. It could be like a really minor point deduction. But I can mostly give you the credit because I can see what you understood. Now for time, I'm going to skip computing this, but again, you could do a similar thing, and simplifying this one I also think is valuable here. You factor out the 3. each denominator is going to be over 4 squared. So you're going to get everything is over 16. So you could factor out the 16 as well. But in any case, when you do all of that, you're going to get 55.875. Okay, so now we've answered 2 parts of the question. So it asked us for the use the trapezoidal rule and the midpoint rule with n equals 4 to approximate the integral. Calculate the error for each method. So first we need to know what the actual value is. If I want to compute the actual error, I need to know what the specific value is. This is a big difference between what we've been doing with Taylor polynomials, because with Taylor polynomials, we couldn't compute the actual error, but we could approximate it. We could get an upper bound on the error. In this case, I'm actually asking for the exact error, and that's why I used a function here that we know how to evaluate. Of course, in any real application, you would never use an approximation technique on 3x squared because you know how to integrate that function. But this lets us examine how these errors work and how these approximations work with something relatively simple, and lets us compute exact errors to get an idea of what's going on here. So in any case, I integrate, I get 3x cubed over 3, which is x cubed evaluated from 2 to 4. That's 4 cubed minus 2 cubed, and 4 cubed is 64. 2 cubed is 8, so I subtract them and I get 56. And we see this is pretty close to the 2 values we got, 56.25 and 55.875. And so if we want to compute the absolute value of the error for the midpoint rule, we just say, well, that's the absolute value of the 56.25 minus 56, which is 0.25. And the absolute value of the error for the trapezoidal rule is just the 56 minus 55.875. And that's going to be 0.125. Okay, so that's reasonably small error. We only used 4 terms here. Obviously, if you're using a computer to do these approximations, you could easily have a computer compute hundreds of terms and get incredible accuracy with this without too much challenge. All right, so let's move on to another approximation technique called Simpson's rule. So Simpson's rule says that the integral from a to b of f of x dx is approximately the Simpson's rule sum s sub n, which is equal to delta x over 3 times f of x naught plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 plus blah, blah, blah. And we alternate back and forth between 2 and 4 each time until we get to the end, which should end with 4 f of x sub n minus 1 plus f of x sub n. So you got to be very careful with this one. It's really easy to accidentally write something wrong. Our middle terms all are going to alternate between 2 and 4, starting with 4 and also ending with 4. And our initial and last term are not going to have any coefficients, or I should say the coefficients they have are just 1. So it's very easy to make a mistake and write this wrong, so be careful with that. Now, another thing to keep in mind is that this rule, Simpson's rule, only works when n is even, and that's due to this formula, right? The way this formula works out, you can't possibly use an odd number of n values, or I should say n cannot be an odd number. And of course, delta x is b minus a over n, and x sub I is a plus I delta x. Now, the proof for Simpson's rule is really cumbersome. So cumbersome that it would add probably 50% to the length of this video for me to thoroughly go through Simpson's rule and also the proofs of error bounds, which we'll talk about next. So I'm not gonna prove Simpson's rule, but I have put a picture up to just tell you what Simpson's rule is doing so that you know, hey, there's no magic here, but it is a little bit messy. You can generally find the proof for this in your calculus textbook, and it's worth looking at to understand what's happening, but it's, I think, a bit too long for the context of a video like this. Okay, so what does Simpson's rule do? Well, Simpson's rule uses parabolas to approximate. And so it turns out that when you have parabolas and you're approximating integrals with those parabolas, you can come up with a nice formula for the values of coefficients for these sums. It essentially allows you to, you can solve for what parabolas act best in a certain sense. And those parabolas are all going to be parabolas that take 3 points on the graph from each subinterval. So when I look at from 0 to pi, I use one parabola here. So the red graph here is our function. This blue portion is one parabola approximating the function. And then the green portion over here is another parabola that passes through these 3 points and approximates the function on this interval. So anyways, you do a whole bunch of mumbo jumbo and out pops this formula. So we're going to go ahead and take a look at this formula and apply it to the same problem we were looking at before. So use Simpson's rule with n equals 4 to approximate the integral and then compute the error. So S sub 4 should look like delta x over 3. Now I already computed delta x and I already computed all the points for the interval, so I'm not going to rewrite all that here. F of 2 plus 4, f of 5 halves, plus 2, f of 3, plus 4, times f of 7 halves, plus f of 4, my last term. So I plug in, I get 1/2 over 3 times 3 times 2 squared plus 4 times 3 times 5 halves squared plus 2 times 3 times 3 squared plus 4 times 3 times 7 halves squared plus 1 times 4, 3 times 4 squared. And now I notice I can factor a 3 out again. Like I get a nice little factor here, 3 factors out. And this gives me 1/2 over 3 times 3 times 2 squared is 4. 4 times 5 squared over 2 squared. The 4 and the 2 squared cancel, so I just get 25. And then here I get 2 times 9, which is 18. And here I get 4 times 49 over 4, which is just 49. And here I get 16. Remember, I've already factored out the 3. Those 3's cancel. And boom, add that all up, divide it by 2, and we get 56. Holy cow, what in the world just happened? There's no error here. I know, I was very excited there for a moment, bear with me. So there was no error, and that should kind of make sense, right? We approximated this parabola with parabolas, so we get the exact value. Now it turns out Simpson's rule is even stronger than that. Can actually give you the exact value for any polynomial up to degree 3, which we'll see in just a moment. All right. So, of course, in general, we can't calculate the exact error if the function doesn't have an antiderivative. So like if we had something like the integral from 0 to 1 of e to the negative x squared dx, right? We don't know how to take that antiderivative, so we can't find the actual exact error, but we have results from the field of numerical analysis that allow us to find an upper bound for the error of a given approximation for a particular function. So that's what we're discussing here is error bounds, upper bounds on the error. So to prove these error bound formulas, you can actually use Taylor series and Maclaurin series, but it's a little bit cumbersome. And again, this along with proving or deriving the Simpsons rule explicitly would make this video really exceptionally long. So we don't really want to dig into that. Otherwise, this would be too much. So instead, we'll just state these and note that, hey, you can get all of these with some complicated computation by using Taylor series. Now, the midpoint error bound says that suppose you can bound the second derivative of x by some number k. So in other words, k is an upper max for the second derivative. In general, we have to find this. We have to go, okay, what's a number that we know this will always be bigger than the second derivative? On the interval from a to b, then if e sub n is the error in the midpoint rule, e sub n is bounded above by that number k times b minus a cubed over 24n squared. And so similarly, the trapezoidal rule says that if the second derivative is bounded above by a number k, then the trapezoid error approximation can be given by, it can be bounded above by k times b minus a cubed over 12n squared. And for Simpson's rule says that suppose the fourth derivative can be bounded by k. So the fourth derivative can be bounded by k. Then the error using Simpson's rule can be bounded by k times b minus a to the fifth power over 180 n to the fourth. And so it's not exactly clear, well, it is clear between the midpoint rule and trapezoidal rule from these formulas that the midpoint rule, we're dividing by a larger number, even though the rest of the formula is the same. So the midpoint rule is going to give smaller approximation errors. And the Simpsons rule formula is a little different because k is computed differently. And you've got b minus a to the fifth power, which if the interval was really wide, could be a pretty big number. But we're dividing by 180 over n to the fourth. So generally speaking, we would expect in most circumstances the Simpsons rule to have a smaller error than the trapezoid or midpoint rule, generally. Okay, so with that out of the way, let's go ahead and tackle an example using this. Oh, actually, wait, before I did that, I wanted to just mention one thing. So Simpson's rule, the error talks about the fourth degree polynomial. And if we take a look at this fourth degree polynomial, or the fourth degree derivative, oh, sorry, folks. I got myself all tongue twisted. Let me start over. For third degree polynomials, I mentioned that Simpson's rule would always give exact answers. How do I know that? Well, again, this result from a numerical analysis says that this number k is an upper bound for the fourth derivative. So let's look at the function y equals ax cubed plus bx squared plus cx plus d. Then its first derivative is 3ax squared. Its second derivative is 2bx, or its second term will be 2bx plus c, and then the second derivative is 2 times 3ax plus 2b. The third derivative, well, 2 times 3 was 6, so this is 6 times a, and then the fourth derivative is 0. And so what that means is k is 0. And if k is 0, then the upper bound using Simpson's rule is 0, right? K times anything. 0 times anything is 0. So anytime you use a third degree polynomial or smaller, you're going to get an exact value using Simpson's rule. All right, so that's hopefully an interesting little tidbit. So now, how large should n be to guarantee that the midpoint rule, trapezoidal rule, and Simpson's rule approximations are accurate to within 0.00001 for the integral from 0 to 1 of e to the x squared? Okay, so again, I'm going to skip some computation here because this video is already a pretty long one combining these two topics. And so I want to not waste any unnecessary time here. So I'm going to skip some of these derivative computations. So f of x is e to the x squared. In order to approximate Simpson's rule's error, I need the fourth derivative. So I'm just going to go through all of those derivatives first. And I'm going to illustrate that when I do my first derivative here, this one's pretty simple. Just get a little chain rule. F prime of x is e to the x squared times 2x. And so when I do my second derivative, I have to apply the product rule. And so I get the derivative of e to the x squared is e to the x squared times 2x times the derivative of 2x, which is 2, plus e to the x squared. Wait, that should be just times 2x. Just times 2x, not times the derivative of 2x. Plus e to the x squared times the derivative of 2x, which is 2. Okay, and then I can factor out the e to the x squared, and I get 4x squared plus 2. And then that gives me another product, and I can do the product rule again. But I'm not going to write all of that out. I'm just going to say the third derivative here works out to 12x plus 8x cubed e to the x squared. And the fourth derivative will work out to 12 plus 48x squared plus 16x to the fourth times e to the x squared. Okay, so that gives me all of my derivatives. And so now I'm also going to find my upper bound for the second derivative and the upper bound for the fourth derivative before I look at each rule's bounds separately. So the bound for f double prime of x on the interval that we're concerned with, which is 0 to 1. Well, how do we find that? Well, we look at the absolute value of the second derivative, which is the absolute value of 2 plus 4x squared times e to the x squared. And this is bounded by what? Well, both of these are increasing functions, which means that they take their largest values, or at least I should say this polynomial is increasing, let's see, yeah, this is increasing from 0 to infinity, and e to the x squared is increasing everywhere, right? So both of these functions are increasing on the interval, which means that the largest possible value is going to happen at the end of the interval. But notice I'm not just plugging in the last endpoint. I'm actually thinking, hey, what do I know about these functions to figure out what values I should use? So I plug in 1 and I get 6 times e to the first power. And now when I look for my bound for the fourth derivative, also on the same interval, of course, (12 plus 48x squared plus 16x to the fourth e to the x squared). Again, I look at these two functions and both of these are increasing. So I know that I can plug in just the largest number on the interval, and that will be my upper bound. So when I plug in 1 here, I get 76 e to the first power. So now when we go to plug in our error formula for the midpoint rule, our upper bound for the error for the midpoint rule is k, the bound on the second derivative, which was 6e, times b minus a, that's 1 minus 0 cubed, over 24n squared. This simplifies to 6 over 24 is 1/4, so this is e over 4n squared, and we want this to be less than, so it said 0.00001, but that's the same thing as 1 over 100,000. So I multiply the 4n squared across and the 100,000 across. I get 100,000 times e is less than, actually I'll leave the 4 on this side, what am I thinking? I'll just multiply the n squared across. That gives me 25,000 and times e is less than n squared. So if I take the square root of that, n has to be bigger than the square root of 25,000 times e. That's a little sloppy. Let me try that again. And when I plug that into a calculator, I get that n is bigger than 260.685. But remember, n has to be an integer. So that implies that n has to be greater than or equal to 261. So that's the number of samples I'd have to take for my midpoint rule to have that accuracy. Okay, now we look at the error for the trapezoidal rule, and it uses the same k value as the midpoint rule, so 6e, 1 minus 0, b minus a to the third power, but instead we divide by 12n squared. So this is going to be equal to e over 2n squared. That should be less than 1 over 100,000. So I multiply the 100,000 across and the n squared across, and what do I get? I get that 50,000 e times e should be less than n squared. So of course n is greater than the square root, then e times, hold on, the square root of 50,000 e. That should all be under the square root there. This should all be under the square root here. And that implies n is greater than. And here, when we plug that into a calculator, we get 368.7-ish. And again, this has to be an integer, so n has to be greater than or equal to 369. And finally, for Simpson's rule, this one has the other k value from the fourth derivative. The upper bound of the fourth derivative was 76 times e. So 76e times 1 minus 0 to the fifth power over 180 n to the fourth. 76 over 180, I'll just tell you that simplifies to 19 over 45. And I lost my e for a second there, and that should have e. Okay, so 19e over 180, or over 45 n to the fourth, right? And this should be less than 1 over 100,000. And that implies 100,000 times 19. So 100,000 times 19, that's a 19,000,23. So that's 1,900,000 over 180 should be less than, or over 45. Over 45. I keep wanting to write that 180. Should be less than n to the fourth power. And I drop that e again. That should be times e. It's very easy to make little arithmetic mistakes on this stuff. Gotta be super careful with that. So then I need to take the fourth root of n, and so n has to be greater than the fourth root of that whole thing. So let me plug that in real quick. And so that gives me n is greater than 18.41. But Simpson's rule doesn't just require that n be an integer, n has to be even. So n needs to be the next even number, which is 20. Either way, you can see here that we get the desired accuracy for our approximation at a way smaller value for n, only needing 20 samples here instead of the hundreds that we need for the midpoint or trapezoidal rule. Okay, I know that was a bit of a long one, so thank you for watching.